All right, welcome. So we're going to go over 7.1 trees. This is out of your book, chapter 7, section 1. By the way, if you don't have access to a printer, you do not need to print this page. It is not necessary. I'm going to walk you through, like I said in class, some of the highlights and important things to get out of this page. So your definitions, main things to know: a network is a connected graph. A tree is a network, so it has to be connected, but it has to have no circuits, which means that every edge is a bridge. A spanning tree, we're going to talk more about later this chapter, but that's a subgraph of the network. It should connect all the vertices and have no circuits. A minimum spanning tree is a spanning tree with the least weight. So we're looking always in this chapter to try to find graphs that have the lowest and smallest weight. As you wrote those definitions on your own, you probably have something different, which is fine. As long as you have the general idea, you do not have to memorize that word for word. Pictures will probably help you out more. So let's go through the pictures. In these first three, this is a network because it's all connected. It's a tree because there are no circuits. Number 2 is a network, but it's not a tree because it has a circuit right there. Number 3 is not a network because it's not connected. This graph is not connected to this graph, and it's also not a tree. If it's not a network, it's not a tree, but it also has circuits. So even if it was connected, even if there was a line connecting like these two right there, it would still not be a circuit, or would not be a tree because you have a circuit. I'll show you the answers to the bottom ones. Again, this one has a circuit. This one's not connected. This has a circuit. That's why none of those are trees. And then the very bottom of that first page, this is a tree. This is not because it has a circuit. This is a tree. Let's go over your answers from the second page. So on the second page, as you notice, I'm show you this figure 1 through 4 at the bottom as well. So notice this is a tree. Every edge is a bridge. This graph is a tree. Every edge is a bridge. So notice the two that are not that way are also not trees. So a rule of thumb, when you're trying to figure out if a graph is a tree or not, if it has a circuit, it's not a tree. If it has no circuits, then it's a tree. As long as it's all connected, that means that every single edge is going to be a bridge. Checking the bottom ones at the bottom. For exercise 4, so this is a tree. All of these are trees. This tree has 5 vertices and 4 edges. You'll notice a pattern. 6 vertices, 5 edges. 11 vertices, 10 edges. 8 vertices, 7 edges. Notice these points right here in the middle are not vertices because they overlap. It's like a bridge, an overpass. So your 3 properties to know. Property 1, in a tree, there is only one path joining any 2 vertices. For example, if you were trying to get from this vertex up here in the top left to this vertex down here in the bottom right, there's only one way to do it, and that's to go here and this way. There's not multiple ways to get there. There's only one way to get there. Property number 2, in a tree, every edge is a bridge. We went over that several times on this page. And then what you learned in this section here, your vertices, which is n minus 1, equals your edges. You could also write that as E equals n minus 1. Vertices, one more than edges. Vertices, one more than edges, every single time. That makes it a tree. I hope that helps. That was a short video, but I hope that helps. And if you have any questions, let me know. We'll be glad to go over it next time.